Space. It seems like it must go on forever. But does it? Out there in the farthest depths of the universe, might there be some place where something turns into absolutely nothing? Scientists are probing the far-flung reaches of the cosmos, trying to detect that outer limit, to find the shape of space. Now, surprising evidence suggests that not only is there a place where the universe ends, but that there might be something lurking beyond it, something unimaginably alien. Space, time, life itself. The secrets of the cosmos lie through the wormhole.
Once in a while, a really big idea comes along, one that completely changes our concept of who we are. In 1543, Nicholas Copernicus proved that the Earth was not at the center of the cosmos. In the 1920s, Edwin Hubble saw that all the galaxies in the universe were rushing away from one another, sparking the idea that the universe had not been here forever, but was created in one explosive moment, the Big Bang. Now another monumental change is upon us. We've long imagined the universe to be infinite in size, but many cosmologists now think the universe is finite. Some believe they even know its shape. If we do discover an edge to the universe, we'll have to grapple with another very challenging and unsettling question. What lies beyond the edge?
Every day on my way home from school, I used to pass a long wall. It was at least twice my height. I had no chance of seeing over it, but I could hear strange sounds coming from behind it. My mind ran wild, imagining what might be back there. Wild animals, outlaws, or some fearsome monster. I would press my ear up against it to try and decipher what it could be. I never did find out, but I never stopped wondering. Neil Cornish is a cosmologist who lives and works in the big sky country of Montana. The only walls out here are fences to keep his horses from roaming off. Neil is the latest in a long line of thinkers to contemplate the size of the universe. The first we know of was a Greek philosopher king called Archytas.
The Greek philosopher Archytas offered an argument for why the universe must be infinite. He said, if I was to go out to the edge of the universe and then extend my staff to here, that would now be the edge of the universe. And then if I was to extend my staff to here, that would now be the new edge of the universe. And if I was to extend my staff out to here, that would now be the edge of the universe. So the universe must be infinite.
Archytas' mental game set the tone for over 2,000 years of scientific dogma. Our universe must be infinitely large and has existed forever. But that dogma is now being challenged.
So one problem with an infinite universe that's not just infinite in space, but also infinite in time, has no beginning, you would have an infinite number of stars. So the sky would be this completely covered in white. Bright, bright, so bright that it would fry you. So when we look out at night, that's not what we see. We see a star here or there, and then essentially darkness all around. So this tells us something. It tells us we don't live in an infinite universe that's infinitely old.
It was our dark sky that inspired a revolutionary idea about the cosmos, that it cannot have been here forever. The Big Bang. A moment where all the space and matter we can see burst into existence, expanding out from a single point. But the Big Bang creates a problem for astronomers searching for the edge of the universe. Because it takes light time to travel across the vastness of space, astronomers are always looking back in time, and eventually, they run out of time.
So when we look out at the stars at night, we're seeing those stars as they were years ago. The nearby stars, maybe a few years ago, looking out across the galaxy thousands of years ago. And going back and back, we see galaxies back billions of years ago. And then beyond that, where we see no more galaxies, 13 billion years ago is the next thing that we've managed to image. And it is the afterglow of the Big Bang.
It's called the cosmic microwave background. and it's a picture of the way the universe looked about 400,000 years after the Big Bang.
The universe is filled with this hot gas, this hot plasma. Light really can't go anywhere. So we can't see any further back, just as we can't see into the sun.
The cosmic microwave background is a barrier that blocks our vision. Behind it, there could be an edge, or perhaps the universe does extend on forever. But no matter how powerful our telescopes become, that domain will never be visible. But there might be another way to discover if the universe has an edge. Jan Levin is a theoretician who uses complex numerical simulations to solve some of science's most challenging problems.
It might surprise you that a game as old as Asteroids can teach us something about the universe, but there's a rule in the game to make a world out of the game that makes sense, where if you exit the top, you re-enter the bottom, or if you exit the left, you re-enter from the right. And that rule makes this world in which you're playing the game, this space in which you're playing the game, a finite space. And that's kind of like the rules we're imagining for the universe.
If our universe is finite, scientists believe its edges must also be linked, that the entire cosmos must act like a giant game of asteroids.
If we could bend this space, we would see that it looks like something more intuitive. Like, for example, if I were to take this menu and apply that rule from the asteroid game, I exit the top, I enter the bottom. That's exactly the same as taking the menu and rolling it up and gluing the sides together. It gives the same effect. And if I could bend this rather too stiff menu, I would try to bend it so that the two edges came together and were glued. And then I'd be making something kind of like, a bagel, a classic New York bagel. And the bagel is glued together, not just like a cylinder, but also around the other side.
Even though the surface of this bagel is clearly finite, no one living in this space would ever run into an edge, so it feels boundless and infinite.
When we live inside the universe, we can't step outside of it. There's no other dimension to look down from onto our three-dimensional universe, so it's harder to visualize. But we can use the rules like the rules that are used in the Asteroids game. And then we add one more rule for three rules for 3 dimensions. Go out the back face, come in the front.
If we do live in a cosmic asteroid cube, there is a way we could discover the edges. Not by flying a spaceship across them, but by standing still and watching light as it wraps around the universe. If the universe were the size of a room, and you stood in the middle of it holding up a lantern, light beaming out from your back would zip out one wall and re-enter the room from the other side. So you'd see an image of your back on the wall in front of you. Looking out to the right, you'd see light coming from your left side. The room would appear to be covered in mirrors. Whichever wall you looked at, you'd see an image of yourself. When we look at the night sky, we don't see this hall of mirrors. But space is so vast, light could take billions of years to loop around the universe. Space and time on this epic scale mean that mirror images would look nothing like one another.
So imagine this corral is our universe. There'll be repeats of this corral ad infinitum, giving an illusion that we live in an infinite space.
But if this corral were just 30 light years across, when I look out there, I wouldn't see myself as I am now. I'd see myself as a 10-year-old boy, because I'd be looking 30 years back in time.
Our Milky Way is around 13 billion years old. It's been around almost as long as the universe itself. Could a distant image of the Milky Way be hidden somewhere in the night sky, disguised the way it looked 5 or 10 billion years ago? If it is, how would we even recognize this youthful twin? This scientist believes the cosmos is a hall of mirrors, that the universe is finite, and that he knows its size and shape.
Imagine if the entire universe was just the size of this room, and that space wrapped around itself, so each wall was the passageway to the wall opposite. Looking around, I would see myself fractured as if by a crystal into multiple copies. And each version would be slipped backward in time. Is our universe a hall of mirrors?
Astronomers have looked for repeating patterns of galaxies for years, looking for evidence that the universe has an edge. But they've never found any. Jean-Pierre Luminet is a senior scientist at the Paris Observatory. He's been fascinated with the shape of space ever since he was a child.
I was always interested in shapes created by nature. And, well, it's a nice idea to imagine a typical snail with a spiral, for instance. And you know there are spiral galaxies, for instance, okay? The question is why these shapes could not be also in the sky?
Jean-Pierre's passion to discover the shape of the cosmos grew from the groundbreaking work of the great Albert Einstein. His theory of relativity showed that space is a flexible fabric whose shape is deformed by matter and energy. Einstein imagined the universe as a flat sheet stretching out to infinity. But there's no reason it can't also be finite and curled up on itself. Jean-Pierre realized he might be able to tell the difference between a finite and infinite universe by thinking of the cosmos as a giant musical instrument. The cosmic microwave background image shows us the universe the way it was 13.7 billion years ago. A hot liquid vibrating with aftershocks of the Big Bang, like water rippling in a bathtub.
So in some way, the universe vibrated like a piano or like a drum. So for instance, this is equivalent of the Big Bang. It's a complicated mixture of many harmonics, okay? And now we have the fundamental harmonics, which gives the pitch, and after the other harmonics are like this, and so on, okay? So the full sound that we can listen to is a mixture of all these harmonics.
But the number of harmonics you can hear depends on the size of the piano.
The size of any musical instrument is finite. And a string, for instance, cannot vibrate on wavelengths larger than the size of the string. So maybe if we observe that the universe didn't vibrate on very long wavelengths, maybe the explanation is that space has a finite size.
When Jean-Pierre analyzed the ripples in the cosmic microwave background, he found that the longest wavelength ripples were indeed missing.
We are surprised because there was missing wavelengths, missing fluctuation, missing low tones, you know, like low notes, very low, like this, okay? They are missing from the cosmic score.
Jean-Pierre's passion for music gave him a profound cosmic insight that the universe appears to be finite. But what shape could it be? Jean-Pierre spends months carefully testing different shapes for his finite universe, trying to make it fit the vibrations of the cosmic microwave background as closely as possible, until finally, he finds the perfect fit. A 12-sided dodecahedron, a soccer ball.
Here in my hands I have two different kinds of dodecahedra. The first one is just an ordinary dodecahedron, namely 12 pentagonal faces arranged in a symmetrical manner. This is a figure known since antiquity. And you see that the pentagons are flat, okay? Here you have a different tiling of the sphere. You see that the pentagons are curved, okay? So this is called the spherical dodecahedron.
If Jean-Pierre is right, the shape of the universe is a lot more complex than a 6-sided asteroid's game cube. The universe has 12 sides, and leaving one face leads you to a matching pentagon on the opposite side, but with a twist.
This edge is exactly the same as the opposite edge. So as soon as you get this point, you re-enter your space on the opposite side, and in addition you have to turn by 36 degrees.
If the universe were a dodecahedron only slightly bigger than Earth, light would zip around it in minutes, and you would see twisted copies of Earth in a dozen different directions in the sky. But if the edges of Jean-Pierre's dodecahedron are billions of light years apart, the distant and faint reflections on them could have escaped the notice of the most careful astronomers. And if the edges lie further than 13.7 billion light years from Earth, we would never be able to see them, because our view would be blocked by the hot soup of the cosmic microwave background. As soon as Jean-Pierre announced his results, Neil Cornish begins looking for signs of his colossal soccer ball. He's a key scientist on a NASA spacecraft called WMAP, which spent 5 years photographing the cosmic microwave background in unprecedented detail.
So here's a possible model of the universe based on a dodecahedron. Inside, we have a balloon representing the visible universe, how far we can see. And if it was like this, where the balloon is much smaller than the space, there would be no signs that we're living in a finite universe. But if the visible universe was so large that it actually touched onto the edges of the dodecahedron, then light would actually be able to travel right around the universe. So now we would have these matching circles on the microwave sky where these two spheres intersect to form a circle. A circle here, matching the circle down here. Now we have looked at the microwave background data from the WMAP satellite, and we haven't seen this pattern of matching circles.
But Jean-Pierre Luminet is not ready to give up his soccer ball universe. His ideas have triggered a scientific battle that spans continents and years of meticulous work. At stake is nothing less than the truth about where we live, where we came from, and whether our universe is alone.
Einstein said, only two things are infinite, the universe and human folly. But he admitted he couldn't be sure about the universe. In fact, we're now faced with tantalizing hints that our universe may not stretch on forever. That there is a point out there where the universe as we know it does not exist. It's an almost frightening thought. But before we try to grasp just what might lay beyond that final boundary, we need proof.
Glenn Starkman is a Canadian physicist at Case Western University in Cleveland. He's taken data analysis to new heights in search of that proof. Call him an information junkie.
The joke about Canadians is that you go to an airport and you put up a sign, free sex to the right and free information on sex to the left, and the Canadians are all the ones that go to the left. I hope I'm not that boring.
Glenn has been poring over cosmic microwave background data from the WMAP probe for most of the past 7 years. Along with Neil Cornish, he's been trying to test Jean-Pierre Luminet's prediction that the shape of space is like a 12-sided soccer ball.
I would have been really happy to find the pattern of circles that the dodecahedron told us would be there if the dodecahedron was small, and we looked for it and we didn't find.
But all of their tests assumed that the edges of the soccer ball universe are closer than the microwave background that blocks our view. Now Glenn believes he's found a way to detect the edge of the universe, even if it lurks beyond the area we can see.
What you have to understand is what is this actual pattern of hot and cold spots that we're seeing on this sphere. And what really is sound waves that were traveling through the universe when it was very young. So you can imagine it like stretching the top of a drum. At the same time as it was stretching it, it was actually making the drum vibrate a little.
Different shaped universes, like different shaped drums, should leave different patterns of vibrations on the early universe.
So what we're going to do is we're going to look at some different shaped and different sized drums. And what we have over here is a spectrum analyzer. And Tom has set things up so that when we make some sound, we're going to get some traces on this computer screen. So let's start with our nice round little drum. Now let's go with our heart-shaped drum. Certainly sounded a little bit different. Finally, we have a star-shaped drum. When we superimpose the patterns of those three small drums, we'll see that they're not quite exactly the same. They have different patterns, and so we can tell the difference between one small drum and another. In the same way, what we're planning to do is use a spectrum analyzer to look at the different sounds that the universe made and to tell what the shape of the universe is.
Glenn's analysis involves such complex mathematics that he imagines it will take years to find the answer.
I will be incredibly excited if we turn out to find Jean-Pierre's dodecahedra. It would be like discovering that the Earth is round, but rather than flat.
But this scientist is not waiting for data to answer this monumental question. Andy Albrecht, a theoretical physicist at UC Davis, is sure the universe is finite. He even thinks he can calculate its size. And he studies the very first moments after the Big Bang, when space was nothing more than a seething, chaotic ball of energy. Suddenly, a process called inflation takes hold. It balloons up the universe at an incredible rate, doubling its size 100,000 times. A fraction of a second later, all space and matter is smoothly spread out. Most scientists believe inflation is still happening today.
The going way of thinking about inflation is that it gives us a truly infinite universe. The inflation itself never ends. The more I thought about what that infinity might really mean, the more I realized it probably didn't make sense.
So Andy began working on a new theory of inflation, without infinities. It's dizzying mathematics, dealing with the laws of physics before the universe as we know it existed. But at its core, it all boils down to bubbles.
A random process starts the formation of a bubble that is our universe. I will be the random process and blow the bubble.
The traditional view of inflation imagines this bubble inflates forever. But Andy now takes the lessons he learned in kindergarten as a serious insight. A bubble can only grow so big before it pops. Andy believes inflation must stop when space gets to a certain maximum size, and his pioneering theory predicts that size.
The universe is actually just about 20% bigger than what we see around us today. When I first started trying out those ideas, it was really difficult to go all the way from infinity to such a small thing, just a little bit larger, just 20% larger than what we see around us today. I actually felt claustrophobic.
But if Andy's new theory is right, and inflation does not go on forever, our universe could look something like this: a large bubble surrounded by a cluster of smaller ones.
Most cosmologists think inflation is the best explanation for the even spread of galaxies across our visible universe. But far out in space, there may be regions where inflation never took place. Find those, and you could be the first to find evidence of the edge of the universe. The eternal dance of light in the night sky. It has fascinated humankind for thousands of years, given birth to gods, myths, and finally to science. But now there are hints of strange movements in the heavens. If they can be verified, they'll be the first hard evidence that there is an edge to the universe.
Sasha Kashlinsky is a NASA astronomer. He claims to have detected a pattern of movement in the heavens so bizarre that it could revolutionize our theory of the universe, just as the Big Bang once did.
We're here at Glendale Golf Course near NASA's Goddard Space Flight Center, and we came here to simulate the Big Bang. So let me try and do that. As you see, the balls just move away from their mutual center.
This even spreading out of galaxies from a central explosive beginning is what astronomers see when they look at the night sky. But Sasha wanted to check more precisely how fast and in what direction galaxies are moving to see if there might be any subtle deviations. He used an effect that can only be seen when clusters of galaxies are colliding. The gases around them get heated to millions of degrees. When light from the cosmic microwave background passes through that hot gas, it gets subtly altered. How much it changes depends on exactly how fast the gas and the galaxies it surrounds are moving. But the change is tiny and almost completely buried in background noise.
For each individual cluster, this is a very tiny amount, and it gets drowned by the noise. But if you have many clusters, you can beat down the noise, but it's exceedingly difficult.
Sasha methodically worked his way through a catalog of galaxy clusters from an orbiting X-ray telescope, checked their precise position using ground telescopes, and then carefully lined them up with a cosmic microwave background.
Oh, we were quite shocked when we saw these results at first. In fact, so much that we didn't know what to do with it. We kept checking and checking. We sat on the data for a year plus, just checking everything because it just didn't make sense to us.
What Sasha's data showed was almost unbelievable. All the galaxy clusters, no matter where they were in the sky, were all veering off to one side of the universe. It was as if they were being pulled toward a mysterious attractor beyond the visible edge. He called it dark flow.
We called it dark flow because the observed distribution of matter in the universe cannot account for this motion.
But if nothing Sasha could see was pulling the galaxies to one side, what could be responsible for the effect? The answer could be the edge of the universe.
If you live in this part of the world, then at first you would imagine that the entire world is as flat as what you see locally. But if you were to look sufficiently far away, you may discover that the world is very different from what you see locally.
Cosmologists, ever since Einstein, have thought of the universe being like a flat putting green that extends on forever. But dark flow could be hinting that our universe is a finite space, surrounded by stranger terrain.
So this was Big Bang on a flat surface. So now let's go to a different part of the world. The balls did indeed disperse, but in addition, they also have another velocity which is associated with the tilt of this surface. They move collectively and systematically from the higher ground to the lower ground.
Sasha's discovery of a collective systematic movement of galaxies to one side of the cosmos has shaken the field of cosmology. Some scientists refuse to believe it. But for this woman, dark flow was entirely expected, and her ideas about the universe are even more mind-bending than Sasha's. She believes she's found evidence that another universe is reaching out and touching ours.
Scientists have discovered a mysterious dark flow of galaxies, all veering off to one side of our universe. It could be a sign that way out beyond the furthest star lurks a portion of the cosmos vastly different from the universe we know. But there's an even more shocking possibility. Dark flow could be evidence of another universe reaching out to us.
That's what theoretical physicist Laura Mersini-Houghton thinks. The seed of this idea was planted many years ago when she realized she had a problem with the universe, a pretty big problem. According to her calculations, the universe should not exist.
The chances to start the universe with the high-energy Big Bang are 1 in 10 with another 10 zeros behind it and another 123 zeros behind it. So pretty much zero. So whenever in science we end up with an answer that this seems very unlikely, this event is not generic, then it usually indicates that we may have blundered in something very basic.
But Laura had an idea of how to stop the Big Bang from being such an unlikely event. You might call it a gambler's hunch. If you're playing a slot machine where the odds of hitting the jackpot are 1 million to 1, you could play all day and never strike it rich. But if all 6 billion people on Earth each play their own slot machine, someone somewhere is going to get rich about once every few seconds. Laura realized that one branch of theoretical physics offered a way to turn the Big Bang into a sure bet. It was string theory. This view of reality suggests that alongside the normal 3 dimensions of space, there are another 7 hidden dimensions wrapped up so tightly we cannot see them.
You start wrapping up those extra dimensions, the extra 7 dimensions. There are so many ways of doing that process. String theorists ended up with not just one 3-dimensional world, but with many, many possible 3-dimensional worlds.
In fact, string theorists realized there were 10 to the power of 500 possible ways to arrange these dimensions. That's a 1 with 500 zeros behind it, a number countless times bigger than the odds against our Big Bang.
The only way we can ask the question about the origins of the universe is if we have a multiverse structure from which our universe is born. A landscape of many possible places in this multiverse where the universe can start from.
If each of these balls of wrapped up dimensions is an energy site where a universe could start, then the odds of a Big Bang happening in one of them is no longer an enormous long shot. In fact, the odds are good enough that Laura's willing to bet this landscape should contain many Big Bangs and many universes. You can think of this multiverse landscape as the biggest hotel you can imagine. A hotel with 10 to the power of 500 rooms, each one waiting for a guest to check in.
Every room would represent an energy site of that landscape. There is an infinite number of people that can try to check in into these hotel rooms. I try to go into a room and I discover that energy site is taken. Someone else is there. Once a universe is born in that energy site, first that energy site cannot be shared with another universe. So I try to go to the next room, until I find an empty room. That room is really boiling hot, so it contains a lot of energy. Once I am in the room, I cannot get out of it anymore. The door is locked. That's how the universe is born.
But if our universe is like a hotel room, shouldn't we be able to detect the presence of guests in the room next door? That earth-shattering evidence could look as subtle as this small blue patch. In 2007, data from the WMAP spacecraft confirmed the presence of a strange cold spot in the cosmic microwave background.
If I have an empty region of space, that would show as a cold temperature region. In the case of the cold spot, the only way such a part of the sky could just be completely, entirely empty, that kind of bizarre behavior of the universe can occur only if there is some other force at work.
Laura believes the cold spot is evidence of another universe right next to ours, its enormous mass pulling on matter at the edge of our world.
If there are some very massive objects in the next room, in other words, in the neighboring universe, then I should be able to feel that gravitational pull, although I cannot directly see it.
But for a theory as radical as the existence of another universe, the cold spot alone is not enough. Laura needs more evidence. And help is at hand. Two scientists are about to join forces in a remarkable endeavor to find the size and shape of our universe and the universe next door.
Is the universe infinite? Or does it have an edge? Or is our universe just one member of a cosmic family of universes, spread across a strange and uncharted landscape? Just a few years ago, even asking these questions was unthinkable. Now, we're close to finding the answer.
Sasha Kashlinsky is convinced that some mysterious attractor at the edge of our universe is pulling on galaxies, forcing them to move with what he calls dark flow. His work is still controversial, and to convince the skeptics, he needs more data.
We hope in a few years to have a catalog of up to 2,000 galaxy clusters in total. And with the new data, we hope that we'll be able to measure the flow to much larger scales.
But Sasha now has a powerful ally. 1,000 miles away, in Toronto, Laura Messina Houghton was refining her own calculations about the edge of the universe when she got a phone call from her mother.
And she says to me, "Did you see the news about something called the dark flow or another? There was a NASA person there." And I said, "No, I haven't." So I went straight into my computer and found out that the team at NASA, led by Sasha Kashlinsky, had reported they had seen the dark flow of structure in the universe. That was exactly in perfect agreement with the prediction we had made 2 years ago. But what made it spookier was that even the numbers, the speed at which those galaxies were moving, and the direction into which they were moving, were in absolute perfect agreement, in astronomically, with our predictions.
Now, Laura and Sasha are both contemplating just how this exotic landscape outside our universe might behave.
I can think of this board as the landscape, the energy sites onto which these wave packets of the universe will eventually settle. Now, I have to send the wave packets through that landscape, through that board, in order to populate it.
Think of this marble as the pulse of energy that triggered our Big Bang. Soon, another pulse of energy comes along. It falls into a different dip, and a neighboring universe is born. That universe is not a place we can ever go. Its arrangement of dimensions will be completely different from ours. But there is one way we can sense its presence. If the two universes are close enough together, their gravitational attraction will pull anything with mass towards their respective edges. That's why we see the cold spot. And that's why there's a dark flow of galaxies moving across the cosmos. This other universe is pulling on ours.
Until about 3-4 years ago, we knew nothing of the multiverse. However, things are changing dramatically on the last few years. Technology is helping us find signatures of the existence of the multiverse.
But across the world of cosmology, the reactions to these scientists' controversial work is mixed. If any one of them is right, the implications would be enormous.
Why do we even care about the size and shape of the universe? That part of the story is critical for our attempts to understand how it all came into being, why it is the way it is, and why we see what we see around us. All these questions have very different answers if we're looking at the infinite story or the finite story.
We'd be able to say, look, here is the universe, this is its shape, and that's where we live.
And that's a revolution in physics, going outside our universe, at least with the power of our imagination, but then that's what makes human beings special.
Every now and again, our perception of the universe and our place in it undergoes a revolution. We used to think the Earth was the center of all creation. For the past century, we've learned to accept that we live in a nondescript region of a backwater galaxy in a universe that is unimaginably vast.
Now it's time for another change of perspective. Our universe itself, once assumed to be infinite, might have to shrink down and take its rightful place as a humble member of a truly giant multiverse, a multiverse filled with universes beyond our wildest imaginations.